The next presentation we have is Neha Prakriya, who is a PhD researcher at UCLA. Let's give Neha a round of applause.
Okay, so I have been working on data efficient training for the last 3 years at UCLA, and I'm going to present all the stuff that we've done with AMD GPUs so far. So our lab is trying to address the high training cost. Over the last few years, if you look at the state-of-the-art transformer models, training them has become more and more expensive because we keep increasing the size of these models as well as the data that's required to train them. So every 2 years, the training cost is increasing by a factor of 750x. Meanwhile, key hardware performance metrics like DRAM bandwidth and interconnect bandwidth have scaled at a much slower pace. And this leads to something called the memory wall. Now, there are many different ways to address this memory wall. Some people are developing better hardware, some are optimizing the kernels and stuff. But in today's presentation, I'm going to focus on the software optimizations that we have done. Our focus is on improving the quality of data that you train on. So for example, if you're training on a bunch of images, we perform some sort of subset selection on them where we identify which parts of this data set that you've probably scraped off the web are important and which are not. Then we pass the selected subset over to the GPU for training. After you perform a few epochs of training, you have statistics for each data point as to how each data point is affecting the model performance and the different loss trajectories. We pass those statistics back to our selections so that every epoch you're selecting better and better points that are improving the quality of the model. And then you can pass your trained model over to your edge devices where you're again seeing a lot more data that you observe on the field that might be different from what you've seen during training. So at this stage, we again perform a similar sort of selection at the edge, and we pass over that subset to the GPU for improving the model. So let's see how we are performing this selection. Our techniques are inspired by the way humans learn. If I gave you these two paragraphs, you might read through both of them and then identify which one you find harder, focus for more time on that, and then move on to maybe just reviewing everything before you go for a test. The second paragraph here has more dates, more facts. It's about a war between two different countries, and the first paragraph is just anecdotal. So maybe you'll find the second one more difficult than the first one. Similarly, between these two examples, one is an advertisement for a bakery versus the other one is some piece of code. Maybe understanding this code requires more effort from your end as opposed to reading the example of the advertisement. And this technique is called spaced repetition, where you read through everything, you focus on the parts that you find difficult, and then you review all of the text before you go for a test to avoid any forgetting. For pre-training, we propose training the model in 3 different phases. First, you learn, so you just sample through the database and see what you have. Then you focus on parts that you're finding difficult, and you keep iterating through this, so you identify different parts that you're not doing well at, and then you focus on them. And finally, you review all the data points and reintroduce them, so that you're not forgetting any of the points that you found easy. We've performed thousands of hours of pre-training from scratch. We've trained models from 300 million all the way to 7 billion parameters. These are the different baselines that we have, and the blue stars are the ones that we have trained ourselves. For example, if you were doing random sampling, you might have to train on up to 50 billion tokens for a 300 million parameter model to achieve reasonable accuracy on common sense reasoning problem-solving tasks. But by selecting more important data points during training, you can achieve chinchilla-optimal models much earlier, the way we have. Similarly, we also compare with previous work on data selection that has been more static in nature. So these works were just analyzing which ones you were finding difficult at the beginning of pre-training instead of the iterative approach that we introduced earlier. For the 3 billion and 7 billion parameter models, we've used the OpenLlama implementations that were trained on 1 trillion tokens. Out of those 1 trillion tokens, we sampled only 130 billion as important and high quality. And as you can see, we also consistently outperform all of the baselines. All these models and the code base are available on our GitHub that I will link at the end. So we are still limited by the scale that we have at UCLA, so we are definitely open to collaborating with the different industry partners here. I'm also interning at AMD this summer, hoping to introduce these data scale selection techniques into the pre-training. The next question we asked ourselves is whether we can have similar selection for performing well on specialized domains. For example, if you want to train a model that's specially for math or code or medicine, then you need to adapt the domain of these general models that you have pre-trained. And so we started looking at data efficiency during supervised fine-tuning. For example, if you train the Pythia models on the Pile data set, you can see that in the first graph, you're able to separate it pretty well. But the minute you adapt the domain to math, for example, you're quite confused. So you do need some amount of selection in the math domain before you can perform well on this subtopic. And here, this work was published in NeurIPS last year. So we trained a small proxy model, for example, something like 70 million parameters on the math instruct data set. We collect and cluster the loss trajectories during that training. And we find that examples within the same cluster exhibit similar trajectories, while those in different clusters have different trajectories. So basically, if you are in the same cluster, you're affecting the model in a similar way, as opposed to if you're in different clusters. We also find that this information is transferable across model scales. So if I observe that a specific data point is affecting the model in a downward trajectory, that same point will affect a larger model of the similar family in a similar way. So this cluster information can be transferred. And we use that fact to select data points from the math instruct data set and train our target model. So here we have the results for selection using a 70 million parameter model. And we select half of the math instruct data set. You're essentially speeding up fine-tuning by 2x. And we evaluate zero-shot accuracy for both in-domain and out-of-domain data sets. Recently, we got access to the MI300X GPUs through the AMD HPC grant. So AMD has been very generous in their donations to our lab over the years. And the first project that we're working on here is an HLS coding assistant for FPGAs. So anyone who has worked with FPGAs knows that you require a lot of domain knowledge, a lot of information about the hardware that you're programming for, and it takes up a lot of time. For example, if you have this really simple code, if you directly run it on an FPGA, it's almost 13 times slower than if you run it on a CPU. And you require all of these pragma insertions or optimizations that the programmer has to do. In fact, this solution space is over 3 million design points. So when you, if there's a novice programmer and you give them this example, there are so many options for them to choose from that this really inhibits the adoption of FPGAs, in our opinion. So our lab has over 40,000 circuit designs on FPGAs over the last 10 years, and recently we have also augmented this data set synthetically. You can find the data set in NeurIPS last year. And our goal is to train the DeepSeek coder model on this data set to develop an HLS coding assistant that tells you which pragmas to insert and what the predicted resource utilization is going to be. Thank you, that's all I have for today. And if you're interested in collaborating with us, please do reach out either on my email or offline. Thank you.
All right, thank you so much, Neha. I appreciate it.